Good afternoon. Let's begin. I hope you had a nice vacation. I talked to some of you already, said it didn't really feel like much of a vacation because you were just finishing projects and studying for exams. So I guess that means you're getting good training for the real world when you continue to answer emails and even when you're on vacation. And it's hard to get out of the rhythm of school sometimes, but I think in 2 weeks you'll probably be feeling more relaxed than you feel now when exams are done. Let's look at a couple of announcements and then we'll begin our lecture for today. Homework 15 is going to be collected on Tuesday in class. That is the hazardous waste assignment. So I gave you some extra time compared to what it said on the course schedule. So I'll collect that in 2 days. And then the next thing that you have on the horizon after that is the project, the research papers. And as a reminder, I've announced this before, but what you should do is print out a paper copy of that research paper. And there's no need to get it like specialty bound or a really nice folder or something like that. That's unnecessary. You can just simply staple the papers together and submit a paper copy, and then you also are required to submit it on iLearn. Mm-hmm. No, in class. In class. Both of them in class.
On the research paper side, it says by 5.
Does it really? On the handout itself? I guess you've got till 5 then. Yeah. So I'd prefer that you submit it in class, but if you really need those extra 4 hours, then those are yours to take. All right? So what we're going to talk about today is sustainability, and that's in chapter 13. One strange thing you'll notice about the textbook is that actually we're going to finish the semester talking just in our last class on Thursday. We're going to be talking about radiation. And the author doesn't put that in the book. It's a whole chapter that's just available online. So what I've done is I've put that on iLearn for you to download, either from the author's website or from iLearn. So I'll mention that in advance just so that you can download it, and if you're reading before the lectures, then you'll maybe get to the end of the book and you'll wonder where the next chapter is. That's because the author posted it online rather than printing it. Any other questions before we move on to the new material? All right. What we're going to talk about today is sustainability. And this is something that they're starting to require a lot of engineering classes to at least mention sustainability just a little bit. And in fact, they're even going to start integrating sustainability into some of the structural courses, believe it or not. Because it's something that ABET requires for engineers to start thinking about green engineering and sustainability, but it makes a lot of sense for it to be included in a course about environmental engineering, which is what we're talking about. If you look at the definitions that are provided in the textbook, it says that sustainable development is the ability to meet the needs of the present without compromising the ability of future generations to meet their own needs. Do you think that society as a whole is doing that now? That our lifestyle isn't harming future generations? Can you think of ways that our current way of living does harm future generations, or at least compromises their ability to meet their own needs? Very good. Deforestation, absolutely. Overfishing? It's like you guys have seen the slides that we're going to have today. Yeah. Those are two of the things I'm going to show you pictures of in just a minute, yeah. So what are other ways that we're using more than our fair share? When you look at, maybe the 7 billion people that are on the world right now, we don't own the world because it also belongs to the people who come afterwards. We could use it all if we all agreed that none of us would have any more children. Like if it's just us and there's no one afterwards, then let's just destroy the place, right? But someone is coming afterwards, and so we sort of have an obligation to leave a little something for the future generations to use. We can break down the resources we're talking about into those that are renewable, or easily renewable, relatively speaking, and those that are non-renewable. And some people will get into arguments of semantics and say, well, everything's a renewable resource, even oil, because if we just wait long enough, then the forests will compress and it'll get pushed underground and it'll just make more oil. But of course, we know that takes a really, really long time. They call that the geologic scale. When something takes the really long time, like producing more coal or producing more oil, it takes hundreds of thousands, maybe millions of years to replenish those resources. But then the renewable resources that we can count on being replenished in just a few generations might be surface water, solar power, wind. Solar power is really easily renewable because there's no way to use more of it than your fair share, because the sun keeps sending more and you can't like reach out to the sun and take too much solar power. The same thing is true of wind. You can't take any more wind away than is currently available, and there's going to be more in the future. Timber, on the other hand, it is possible to do damage to the forest such that even in a few generations it won't be replenished. If you damage the soil and you damage the streams. And so timber, we have to be a little bit more careful about extracting a sustainable amount of timber. And the good way of doing that is, instead of clear cutting an entire forest all at once, the more sustainable forestry will take out trees, and so that they're sort of thinning the forest instead of clear cutting it. So we've talked about non-renewable resources, and those are the ones that once they're gone, they're gone. So let me show some pictures here. I've told you before that I'm from a place called West Virginia. And one of the resources that gets used a lot in West Virginia is coal. It's one of the historic things that people have done there, is they've mined coal. And in the olden days, what they'd do is they'd burrow underground and they'd find a seam of coal, and then they'd bring it to the surface through tunnels. And that has given way to a new method of coal mining that's called mountaintop removal. And so mountaintop removal is exactly what it sounds like. They find coal someplace, and rather than making a tunnel, they just explode the mountain part of it, and they throw the top of the mountain that doesn't have coal into a ditch, and then they just haul away the coal in trucks. And so they keep going lower and lower as long as there's coal, and then when there's no more coal, they throw some grass seed on the area and drive away. And they say that they sort of are replenishing the natural habitat, but really they're not. They're just throwing some grass seed on top of like acidic rocks, and they're not really restoring the area to what it used to be. What it used to be was previously beautiful forests, and then what they turn it into is acidic, denuded, barren wastelands. So that's one problem that we have in West Virginia, is mountaintop removal. I'm going to show you several other slides, and I want you to think about, environmentally speaking, what do each of these problems have in common? Deforestation. This is a picture of the Amazon rainforest. Okay, so I guess both of the pictures so far have had trees in them. That's maybe one of the common factors there, but we're not quite through all the photos yet. One of the reasons why they will have this problem of burning the Amazon is because they're looking for more farmland. You know, sometimes the crops exhaust all of the nutrients in the soil, and so then they have to move to a new location that has rich nutrients so that the crop yields can be high. Here's a photo that represents overfishing. This is a very, very large net, and in recent years, as we've harnessed fossil fuels, we've made it possible for ships to go out and tow really large nets that, you know, in the time of sailing ships, it wouldn't have been possible to tow a net. Number one, because you just didn't have the power to get that much force of dragging the net and all the fish through the ocean. But then the other thing was that it was sort of unpredictable, wind power. You never really, you couldn't chase down these large schools of fish that nowadays we have sonar that can peer into the ocean and can tell us where these large schools of fish are. And I think everyone's probably aware of the fact that fish populations have plummeted in the last 100 years, that in some species we've only got about 1% of the fish population that existed 100 years ago. So the fish stocks are kind of collapsing. Here's a picture of a lovely river. I think this one is in Indonesia. And doesn't look like the sort of place that you'd want to use as a drinking water source. But as I was looking for pictures of this on Google Earth, a lot of the photos I saw were of people bathing in this river. And so, you know, I guess when you're dirtier than the river, then you bathe in the river and hope for the best. Hope that it doesn't have too many carcinogenic contaminants and biological contaminants. Of course it does. This is a photo I took when I was in Kenya 2 weeks ago. This is one of the largest urban slums in the world. And a lot of the people who are living in these areas live on less than 5 dirhams per day. I mean, that's their whole budget for the day is 5 dirhams. And so think about if you're spending 5 dirhams and you've got to buy food, power, transportation, health care. And think about what you'd be able to afford if your budget was 5 dirhams per day. Probably you wouldn't spend it on a Starbucks, right? You wouldn't save up 3 days so that you could afford a Starbucks. No. How much is a Starbucks? I don't drink coffee. How much? 15? Okay, so you'd have to save 3 days and then you have a cup of coffee. Maybe your priorities would be different if that was the budget. All right. So what do they all have in common? People. People are sort of the cause of the problem. Too many people. Let's not say that it's people. Let's say it's too many people. That's how the book puts it. The book refers to the population problem, the people problem. And the issue is that we keep having more and more people on the same size Earth. Our planet isn't growing at the same speed that the population is growing. In fact, the planet's not growing at all. It's the same size. You know, we live in a black box. And sometimes in environmental engineering, remember how we have flow in and we have flow out, and then we say, you know, here's a black box and it's our CV, which stands for control volume. And let's keep track of what's flowing in and out of the control volume. Well, our planet is inside of a black box, and there's nothing really coming in or out. I guess there's sunshine coming in, but oxygen stays in the black box. A lot of our resources are fixed, but our populations still are growing. And this is a figure that demonstrates what year we cross the billion mark, the 2 billion mark, and so on. In the book, it describes population growth according to an exponential model. And here is the equation that we use for exponential growth. K, the growth rate, one sort of a rough way to estimate the growth rate of a population is to look at the birth rate minus the death rate. And usually birth rates are expressed in terms of people per 100,000. And so how many births are there per 1,000 of population? And death rate is expressed in the same way, deaths of the whole population per 1,000 people. And you subtract the two in order to get the overall growth rate. For an individual country, you can also have immigration and migration, which can increase or decrease your growth rate. But on a planetary basis, so far we haven't had anyone immigrate out of our planet or immigrate to our planet from outer space. So it's just the population birth rate minus the death rate that gives us the overall K. I've given you a handout today, and what we're going to do with that is take a look at, you know, according to this exponential model, we can see from the figure that in 1927 the world's population was 2 billion. So in part A, I'm going to ask you to apply this model. And remember, models are just meant to approximate reality. They don't always get it 100% right. So we're going to see if we use this model and an annual birth rate of 22 per 1,000 people and a death rate of 5.3 per 1,000 people, according to this exponential growth rate model, what should be the year that we get 3 billion? So what you're going to have to do is calculate K and then substitute it into that equation to solve for T, and then T will be a number of years, and add that to 1927, and we'll get the predicted year. So this is like first order kinetics, right? And so, you know, the K has units of inverse time. And if you've ever wondered, you know, why is it that first order kinetics has like hours to the -1 or days to the -1? The growth rates are, you know, 22 births per 1,000 people. So that's people per year. People divided by people per year. And so the year is in the denominator there, and the same thing with the death rate. 5.3 people die per 1,000 people per year. So the overall net growth rate here is 0.0167 inverse years. And you can see how the substitutions go from there. So it'll happen during 1951 if this population really is behaving according to first order kinetics, if it's an exponential growth model. What does the graph say it actually happened? So this is predicting 1951, but it actually didn't happen until 1960. So what does that tell you? It tells you it's not accurate, that something changed between 1927 and 1960. It's not that the growth rates are wrong. Actually, those are the correct growth rates if this was first order. Yeah? Yeah, it could be. You know, think about what really happened during that time. There was a world war that killed literally millions of people. And so first order kinetics doesn't account for that. So we had a lot of deaths due to war, and then there's also the fact that you know, people aren't bacteria. You know, bacteria may behave according to first order kinetics, but humans are more complicated than just replicating as much as we possibly can, having as many children as the food supply will permit. And so we're going to talk about population decline in just a moment. Okay, so part A was what year would it take to get to 3 billion? Reality was 1960. According to this first order model, it was saying it would be 1951. So part of the illustration here, the point is to get familiarity with this model, but also it's to get some experience with the fact that models don't always represent reality to perfection. Sometimes reality is more complicated than a single equation, because that equation doesn't account for things like war or people getting more wealthy and therefore having fewer children. All right, B. What would be the population in 1974? Well, it depends. I started back with 1927 as the starting point because that was the known. That's when, you know, it was given that the population was 2 billion. And so if we had 47 years according to that growth rate, this is saying that the population growth would be up to 4.4 billion approximately, and in reality, the data told us that in 1974 it was 4 billion. And so again, the model is overestimating. It was saying we'd be at 4.4 billion. Really, we were just at 4. Any questions about the in-class exercise? The calculations? All right. Well, let's look more about how the growth rates decrease. Back in 1980, they started to look at this population problem and trying to predict where does it go from here. You know, are we going to have a constant path of just ever increasing populations where, you know, everyone who's born has 5 children themselves and each of those 5 people have 5 children on their own and so on? Or is it possible that the fertility would be reduced? And so they came up with these different predictions, a rapid reduction in fertility and so on. And so where we're at now puts us on this course of the moderate fertility reduction path. You know, like one of the predictions they had is that people would have a moderate reduction in how many children they'd have. And if you look at where we are today, 2016, the population is 7.2 billion, and so that puts us on the moderate path. And in fact, what they're estimating now, where we're headed, is that by the year 2050, the population will be somewhere between 9.1 and 9.2 billion. And that's the range of estimates they have for what we'll be at in 2050. So I guess we can feel somewhat relieved that the fertility is tapering off, but still, if you think we've got a lot of pollution now with 7 billion, think about all the extra pollution that's going to be caused by an extra 2 billion people, especially because most countries are getting more wealthy. Why does that matter? Why should we be concerned with the fact that countries are getting more wealthy? More supply of what? Of food, all right. So when you get more wealthy, one of the trends that has been noticed is that usually when people have more money, they eat more meat. And meat has a big environmental impact because cattle eat a lot of grain. And so either we can eat the grain and we only need a little, or a cattle is going to be eating grain for its whole lifetime, and then people eat the cow. And so there's a higher embodied energy in meat. And then the other issue is that the waste of the animal pollutes the atmosphere and water. And so when we're rich, we use more electricity, we use more food, we generate more solid waste compared to societies that have less money. So not only are we going to have more people, but those people are going to be wanting to have cars and air conditioning. The quality of life is always getting better, and invariably that means more consumption of resources, not less consumption of resources. So here's an interesting map that shows fertility as a function of country. And so you can see, according to the scale here, the countries with lower fertility are those that are in like the blues and the purple colors, and then the high fertility countries are the ones that are more red and purple. One of the news stories related to population is that there are some countries actually that are feeling very threatened by the possibility of population decline. That although the Earth's population as a whole is going up, there are some countries where their population is going down. It's not just that their fertility is decreasing, that they're actually losing people, that there are fewer people living in the country than there used to. Russia is one of those countries, and this particular article, as I read through it, it said that one of the main reasons for Russia's population decline is that people are becoming less healthy in Russia. That it's actually one of the few industrialized countries in the world where death rates are increasing instead of getting better. And it was saying that throughout the fall of communism in the 1990s, that the rates of liver disease skyrocketed. And they attribute that to, people were drinking more alcohol because they lost their job, and so they're drinking more, and then, that all of those things snowball into worse health outcomes. And so that was one analysis of the population problem in Russia. Another part of it is just that people are having fewer children than they used to. And that's a huge part of Japan's population problem. And one of the issues with Japan, it's not that people are living shorter, it's that in Japan they're living really long. They have one of the longest expected lifespans in the entire world in Japan because they have very healthy lifestyles there. And so one of the concerns they have in Japan is, who's going to take care of the older people? Because you have lots of old people. The young people nowadays are having fewer children. And so one of the main concerns they have in Japan is, even if you've got enough money in your old age, if there's no one to make the food and produce the services, you can't have a good retirement if there's no one willing to accept all this money that you've saved years and years to accumulate. This article was explaining the population crisis in Japan arising partly from the fact that people are choosing not to get married anymore. That in Japanese culture, it's customary for women to stop working once they get married. And nowadays, women don't want to give up their jobs, and so they're less likely to get married and therefore less likely to have children. So it's kind of interesting how, you know, events in history, like the fall of communism in Russia, and changes in attitudes about work can affect population issues. Any questions or comments about this before we move on? All right. I guess one other trend, I think I mentioned it already, that as we get richer, we consume more. You know, we use more electricity, we have more cars, and so on. But also, it's been noted that as societies get more wealthy, they have fewer children. Why do you suppose that is?
Because they are busy.
Okay, they're busy.
Usually in poor countries, they like.
But wouldn't you be really busy if you had 6 to 7 kids? That would make you, I think, more busy than having a job.
But you don't have jobs today.
Sir, I think education.
Education? That could be partly it, yeah. All right. So it's in more developed countries, the cost of children is high. Yeah.
Poor countries, like, they don't really care about like things they do.
They need more kids to provide their father sometimes work.
Yeah.
Farming.
Right. Yeah, children are the retirement plan, actually. I mean, if think about the people who are living in the, I showed you the pictures of the slum in Kenya. The people who are living there aren't going to have a big savings account balance at the end of their life because they're just scraping by on 5 dirhams per day. And so their retirement plan is that their children will take care of them when they're grown. And so in a country where you have a social support network and benefits, then you don't have to worry about having kids to take care of you. There are other ways that you're going to have security in your older years. So I think it's probably a little bit of everything that was mentioned already, along with the fact that maybe you have the children you want and not the children you need once you live in a country that's a little bit more wealthy.
So, what is number?
How many? Yeah, it's the average number of children that each couple has. And so if you live in the United States, the average is between 1 and 2 children. If you live in Mexico, the average family has 2 to 3 children, and so on. Yeah. That's a good question. I'm not sure, because you're maybe wondering about the UAE, right? Yeah, because there's a lot of workers here who don't have families with them, and then some families who are here. And I'm not sure. I think that the Gulf area is probably unique in having that situation where there's a lot of people that aren't having families, but I don't know. If I had to guess, I'd guess that it's probably looking at the citizens, because it would be even lower than 2 to 3, I think, if it was factoring in everybody, but I don't know. Sudan? So for Sudan, it's showing 3 to 4? Do you think it's higher than that or lower? Yeah. I think it's probably more recent data than that. It's not like an average over the last 20 or 30 years, but yeah, maybe what we notice is our own families, right? I have 3 brothers and a sister, so in my family there was 5. But the United States average now is 1 to 2. So maybe we think of the people that we know, not the people who are having kids now. How many kids do you have, right? Most of you none? Probably all of you none, right? So, all right.
But sir, usually in some like poor places, there are many people that they are not adjusted to the government's books.
Yeah.
So, like I think in Egypt they have this problem. So
Mm-hmm. How do they keep track of populations in places like that? I don't know. I don't know. I think that they can estimate populations in a lot of ways, not just actual head counts. They can look at how much food is being consumed. They can look at how much electricity is being used and maybe extrapolate population from that. All right, so the next thing the book discusses, after we move away from the issue of population growth, it talks about green engineering. You know, trying to adapt to the fact that the planet is overpopulated. So how can we overcome that problem? Partly is by focusing on engineering. You know, just engineering in general is this: the design, commercialization, and use of processes that are feasible and economical. So if we stop there, that's traditional engineering, designing things, making it economical. But green engineering goes a step beyond that and says that we should reduce the generation of pollution compared to the old ways, and also we should minimize the risk to human health and the environment. So that's the definition and the two main elements of green engineering. And so the pictures you can see here, this is a photo of what's called a green roof. And this is becoming more common to have buildings that have plants and soil on the roof. It provides some benefits. For example, if there's plants, obviously they're releasing oxygen and taking in carbon dioxide, and so it's a sink for carbon. But then the other benefit is that it helps to reduce stormwater runoff, so that on a day like today when it's rainy, the water falls onto the green roof and it slows down how quickly it gets to the storm drains, because sometimes those storm drains get overloaded, especially in big cities. Of course, wind power is another good example of how we can generate electricity while minimizing pollution. The next of the issues raised in the textbook is the relationship between water resources and sustainability. And the book starts off that section by talking about climate change. And for the next several slides, I'm going to be showing you figures that relate to the United States. And the reason for that is because a lot of really good data is available for the United States. And it's not that these trends are only happening in the US. The same trends are happening other places as well. It's just that there's lots of airports scattered all over the United States. Each of those airports has a really detailed weather station, and there's other weather stations as well. And so it's good to sort of learn about the trends by using the US data, because the figures and the data already exists for a geographic area. So what this is showing is that the climate is changing, and one of the ways that it's changing is that weather events are getting more extreme. I learned that last winter when we had a relatively mild winter. It was going fine, and then suddenly the temperature dropped, and we were having temperatures like -15, -20 Celsius, and that usually doesn't happen in West Virginia. I mean, it was just, they called it a polar vortex. It was out of control cold. And so having these strange extremes has partly been manifest by increases in heavy precipitation. Instead of having a little bit of rain all through the rainy season, what's happening now, we're finding, is that there's just these huge storms that hit very hard, very quickly, and then nothing. And so an increase in heavy precipitation is dangerous from an engineering perspective, because the things that we size, like culverts and bridges and canals, we were expecting that the rain trends would continue like they have in the past. We've done a lot of designs based on statistics from dozens of years ago, but now the pattern is changing. And so we have to adapt a lot of engineered systems to react to climate change, and it's not just precipitation. Another one of the big changes that's happening is that there are more places across the world that are experiencing drought, which is a shortage of water. And this is showing the US drought monitor as of just a few days ago. As of a few days ago, California is experiencing really problematic drought. It's mostly in the western parts of the United States, although you can see there's some isolated parts in the eastern part of the US that have a little bit of abnormally dry. But like the real problem areas are in Nevada, California, Oregon, the western part. This extreme drought, what it's causing to happen is that they're having to consider water resources that they've never done before. Like here in the UAE, we just sort of take for granted that most of our water comes from desalination. But they are just starting to make that a reality in Southern California as well. They're in the process of just opening up a really large, at least relatively for the United States. Worldwide, the new desalination plant that they're opening in California won't even be on the top 10 list compared to other places throughout the world. But they haven't had to do that in the past, but they're running out of renewable water resources, and the population is getting too large in some of these places. So let me show you a map of aquifers in the United States. And of course, an aquifer is just an underground area where all of the voids in the soil are full of water. And what I've circled here is called the Ogallala Reservoir, the Ogallala Aquifer. And it's significant because in this area is where a lot of wheat and corn is grown. And actually, the United States accounts for 40% of all the corn that gets exported in the world. And so, like, this region is important not just to the United States, but worldwide, because a lot of wheat and corn and sorghum comes from this area. But the problem is that there's not enough rain for the crops that they grow there. So since there's not enough rain, they have to drill wells. They drill down into the aquifer and pump the water out. Unfortunately, they're pumping out the water more quickly than it can be replenished. You can see from the screen there that they only have 2.16 centimeters per year that's infiltrating into the aquifer. Now, of course, it rains more than that. It's just that a lot of the surface here has very fine particles of soil, so the water doesn't penetrate very easily. So they're having a recharge of 2 centimeters per year, but withdrawals of about 5.5 centimeters per year. So the water level in those aquifers keeps getting lower and lower and lower. And the same thing happened here in the UAE. Actually, you know, the UAE has had significant groundwater resources, but the majority of those have been depleted, and there's only a handful of aquifers that still exist, because when out is greater than in, there's a negative accumulation, which means the levels will decrease. So here's an illustration of that decrease in New Mexico. There were a few years when they weren't monitoring the depth to the water table, but you can see in the past, back in 1986, they only had to go down about 150 feet from the surface to get to water. But nowadays, they have to go down 500 feet to get to water. And so that makes it a lot more expensive to pump the water, because you're lifting water a greater height. That adds to the electrical cost. But the more critical concern is just you're going to run out of water eventually. You won't be able to pump it out if it's not there. The water levels going down also causes changes in the land itself. The land starts to collapse where the water has been withdrawn. And so that can cause subsidence and fissures in the land and structural issues. This particular fissure was taken, it's a photo from Edwards Air Force Base, which is where they used to land the space shuttle. And so they actually had to close one of the runways that the space shuttle could land on, because this gigantic fissure that was caused by land subsidence because of excessive withdrawals of groundwater. And we've already talked about agricultural productivity, that if they're not able to continue growing those crops, then there's going to be a shortage of food on the world market at the same time that populations continue to increase. So I've already showed you the picture of drought, and here is a representation of places where the groundwater levels are going down. You notice that there's an overlap there. It's not that the over-pumping caused the drought, but it's sort of the other way around. It's that California, Arizona, Nevada, those places are always chronically dry, and so they get accustomed to pumping the water from underground, and so they sort of got into a loop of always using more water than was available, and so the water levels kept getting lower and lower over time. So San Diego is one city that's gotten a little bit more aggressive about trying to respond to drought. And they have a series of different steps they take when there's a drought. When they notice that there's just a slight drought, they start to ask people to restrict the amount of water that they're using. They don't allow washing of paved surfaces when they're in a level 1 drought. You can see it progresses to the point where in the worst drought, if they need to reduce their demand by 40% or more, then they tell everyone that you can't water your lawn anymore. No more grass. You can only water the trees and the shrubs. Why do you suppose they allow people to continue watering trees and shrubs, but not grass? Yeah? Grass demands more water. That's part of it. And then the other thing is that grass comes back more quickly. You know, if you allow the trees to die, then it can be 80 years before you have a mature tree again. And so they make allowances for how long it takes to grow the thing back again. So the green engineering response to water scarcity includes things like drip irrigation, which is so much more efficient than spraying water into the air. So if you're spraying water into the air, it evaporates, especially if you do it during the daytime. But if you allow the water drop to go straight to the soil very slowly, then you're only providing as much water as the plant actually needs, and you're having much less evaporation. Another good way to conserve water resources is to not just water a fixed amount every single day. Like, I'll be interested to know if they water today on campus. You know, we've just had loads of rain, but there are people whose job it is to turn the water on, right? So I don't know if they'll rain today or not. Has anybody seen if they're irrigating? Yeah. Take pictures if you notice people watering today, all right? The other way of doing it, smart irrigation, uses sensors to look at if it's been raining, what's the humidity, maybe a soil probe that actually says how dry the soil is getting before you make the decision to water. Last thing I'll mention is rainwater harvesting, which is a way of just capturing water that normally would go into a storm sewer and using it as a resource rather than treating it like it's waste. All right, we won't get to the next part of the in-class exercise. That was just to ask you, think about the local area and how is water used. So on your way out, please put your in-class exercise paper onto the chair, and let's just take one last look at the announcements here. A reminder that the assignment is due on Tuesday and the project on Thursday by 5 p.m.